Okay, welcome back to our next video in Unit 5. This is video number 3. We're still looking at algebraic limits. We left off on page 10, and we had just done question A and B in the practice ones. So I'd like for you to maybe look at one more, and then the other ones I'm going to leave for you to try. All of these here, C, D, E, and F, again, if you try direct substitution first to see what you end up with, you might end up with a reasonable answer, and if you do, well, that's your limit. But if you don't, if you end up with 0 over 0, all right, remember that the technique that you try is some kind of algebra. Usually, it would involve factoring and canceling if possible, and then trying direct substitution. There are a few cases, though, and I might look at some other ones with you a little bit later. There are some cases where it might be advisable, if factoring doesn't work, to try something else involving algebra. So, for example, maybe multiplying the numerator and denominator by a conjugate of some of these expressions. Sometimes that works. So let's have a look at C. I'll try this one here. If you plug in 3 again by direct substitution, what will you end up with? Well, you'd end up with 3 squared minus 2 times 3, subtract 3, divided by, and in the denominator, of course, now all you'd have there is 3 minus 3. So you can see right away you're going to get 0 in the denominator anyway. But if you take your calculator and just evaluate the numerator, 3 squared is 9, take away 2 3s is 6, so that becomes 3, take away 3, look at that, by golly. 0 over 0 again. So as soon as you see that, you try something involving factoring if possible, and canceling, some kind of algebra anyway. So let's see what would happen here now if I did that here. I get the limit as x approaches 3. I always write that symbol down until I actually plug it in. All right, let me see. I have a trinomial in the numerator, so that could possibly factor. What will that factor into, I wonder? It's going to be x and x. Signs are different because of this minus on the end. So one's a plus and one's a minus. And numbers that multiply to give me 3, well, there's not a whole lot of choices there with regards to integers. It has to be 3 times 1. But remember, you want to end up with minus 2x in the middle. So the only way you're going to end up with minus 2x is if you put the 3 after the subtract and the 1 after the plus, and now you check your middle term, all right, to see if this actually gives you minus 2x in the center. X times negative 3 is negative 3x, and positive 1 times x is just positive x. Add those together and you get negative 2x. So I know that I've done that factoring correctly. The denominator, of course, is also x minus 3. Now, do you see anything there that you can cancel? The answer is yes. The x minus 3's will cancel because they're like terms, like factors. And now if you try direct substitution into the result, all you have left is x plus 1. So now if you plug in a 3, you're just going to get 3 plus 1. So it turns out that the limit is actually 4. Look at that. That's a real number. That's a reasonable answer. That's what the limit would be for that function. Now remember, the point 3 and 4, when x never does exactly equal 3 because it's not allowed to equal 3. 3 is not in your domain. But as it gets closer and closer to 3, the y value gets closer and closer to 4. That's another one of those graphs where you have a hole in the graph because it's a removable discontinuity. Now, I'll leave D and E and F for you to try. You go ahead and do those. But they should be very similar to the ones we've already looked at. Make sure you check the answers as well on D2L. Question number 2 on the bottom of page 10. Now, all they want you to do there is sketch the graphs to assess the limits. I'm going to leave those for you to try as well. Feel free to use Desmos if you like, www.desmos.com, or if you wanted to, you could even use some other form of graphing technology. There's all kinds of apps that you can download for free that I'm sure would graph those no problem. And once you have the graphs, then check to see what the limits are, okay? I don't think these would give you 0 over 0, by the way. All right, they wouldn't. So you can check those graphs. Question number 3 on page 11. Now this is what we call a piecewise function. You've seen these before as well. It says determine the left-hand and right-hand limits of the piecewise function as x approaches 0. So this table right there shows as x approaches 0 from the left, and you'll note that as x approaches 0 from the left, well, it's getting closer to 0, yes, but they're negative values, aren't they? Negative 0.01, negative 0.001, and so on. And what's going to happen is, use your calculator, just plug them in to the function. Now make sure you plug them into the right piece. Here's the piece there that refers to values of x that are less than 0. So as x approaches 0 from the left, that's the piece that you would use. Well, these numbers right here, if you plug them into your calculator, what's going to happen is they're going to start getting closer and closer and closer and closer to 1. That's what's going to happen. So the limit as x approaches 0 from the left is 1. Now, this table refers to x approaching 0 from the right-hand side. So now your x's are a little bit bigger than 0. And that, let me just change my color here. This table would refer to this piece of your piecewise function. All right, so if you plug those values of x in, now notice that this time the x's are positive, but they're still getting closer and closer and closer and closer to 0. All right, 0, 0, 0, 1. You plug those in, and now here's what happens to your graph. Here's what happens to the y value, I should say. The next value is going to be negative 0.99, negative 0.999, negative 0.9999. Now what does that look like it's getting closer to? Well, negative 1. So even from the table, you can tell that the limit from the left is not going to equal the limit from the right, and therefore the limit does not exist. That would be your conclusion. Now here's the graphs anyway. And I mean, it's quite obvious from the graph that the limit from the left, okay, as x approaches from the left-hand side, the y value it's getting closer to is 1. As x approaches 0 from the right-hand side, it's getting closer to negative 1. In either case, the limit does not exist. All right? So that's a nice little one using a table. I've actually had quizzes and tests with tables in them like that. And students have had to evaluate the limit just from the table. No graph, no function, just a table. Okay, let's go to page 12. And now here on page 12, here is where we get into the case that we mentioned just a moment ago. You've actually seen these graphs before. All right, using a graphical approach, you can tell. Let me just change back to right here. If you look at this graph there, for example, well, this is the function 1 over x. All right, you see that? Now, as x approaches 0 from the left of 1 over x, you can see that it approaches, the y value goes to negative infinity. As it approaches 0 from the right of 1 over x, that would be this piece, well, it approaches positive infinity, and therefore the limit does not exist. Now, that's how you did it with a graphical approach. 1 over x squared, though, is different. Look at this. Watch what happens to 1 over x squared. They look very similar, but the result is completely different. Now, as x approaches 0 from the left, if you had the graph, you can see that it goes to negative or positive infinity, the y value does. And as x approaches 0 from the right-hand side, it also approaches positive infinity. Now, you still have your asymptote there. The y-axis is your asymptote. But because the left-hand side and the right-hand side are both going to the same place, they're both going to positive infinity, then the limit does exist, and it's equal to infinity. Now, that's what you would do for a graphical approach. But what if you didn't have a graph? What if you didn't have a graph? These examples here on page 12, they want you to evaluate the limit as x goes to 0. And by the way, I'd like to point out that the fact that x is going to 0, that's not what's important here. It's not what x is approaching, it's what result do you get, what answer do you get if you try direct substitution. And in this case, whenever you try direct substitution, you always end up with some kind of a number, some non-zero number, but you do end up with a 0 in the denominator. So that's what's happening here. There's a 1 in the numerator, but it could be any number, really. So I'm going to show you a technique here now that you can use algebraically. Now, whenever you do get a result, when you try direct substitution, if you get a number over 0, like that, then you always have to evaluate the limit as x approaches from the left, and you also have to evaluate the limit as x approaches from the right, whatever the value happens to be. Now here there's 0, but really it could be any number. All right, so watch what we're going to do here. If you just try direct substitution like I mentioned that you should try, you're going to get 7 over 3 times 0 to the power of 4, and by golly, that's 7 over 0. So what in the world is that? What does that give you? That's not 0 over 0, remember. So factoring and canceling here would not work. And in fact, if you try direct substitution with all of them on that page, you get some kind of a number, any kind of a number, over 0. So watch what we have to do. Watch what we have to do. Now you only have to take the limit from the left and the right for these cases, okay? So step number 1. Step number 1. The limit as x approaches 0 from the left side. Let's do the left first. Of 7 over 3x to the power of 4. Now watch what I'm going to show you. We're not actually going to put in direct substitution here, but I want you to think about the kind of numbers that x is approaching. As x is approaching 0 from the left-hand side, we're talking about numbers like negative 0.00001 or something like that, something that's very, very, very close to 0. But what happens is if you plug it in here, right there, all right, you end up with 7 over 3 times a very, 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 very tiny number, a negative number, raised to the power of 4. Now, my old calculus teacher back in university used to do this. Watch this. That's going to be 7 on the top. Now, the bottom is going to become very, 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 very tiny, very small. But the thing is it going to be a very small positive number, or is it going to become a very small negative number? Because it makes a difference. That's what you're looking for. That's the main idea. Well, a negative number, any negative number, raised to the power of 4 becomes positive. 3 times a positive number, well, it's still small, but the fact of the matter is it's positive. All right? So, what is that? What does that go toward? Well, any number divided by a teeny, 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 tiny number, you take your calculator and you try something like 7 divided by 0.000000001. Put in a whole bunch of zeros and try that with your calculator. You're going to get back a huge number. Huge. And the smaller that number gets, there in the denominator, the bigger your result gets. In fact, it goes toward infinity. But is it positive infinity or is it negative infinity? Well, look at what you're dividing here. 7 is positive. The denominator is a small but positive number. And a positive divided by a positive, everybody, is a positive result. All right? So that goes toward positive infinity. That's what it gets closer to. Now, let's try the same thing. We know that this piece, as x goes towards 0 from the left, the function goes toward positive infinity. Now, let's try, here's my second part of the calculation. What's the limit as x approaches 0 from the right-hand side of 7 over 3x to the power of 4? Now, just think about what kind of numbers you're thinking of putting in here now. What is x approaching? Well, those kinds of numbers would be something like, again, approaching 0. So it's going to be very, very, very tiny, but it's approaching from the right-hand side now. So this is positive 0.0000001. And if you were to plug that in by using direct substitution, think about what you would get. The numerator is still 7, isn't it? The numerator is still 7. If you put in that little teeny tiny number in here for x, raise it to the power of 4, well, it gets even teenier and tinier. You multiply that by 3, it's still teeny tiny. It's going to be a very small but positive number again. So what happens is 7 divided by a teeny tiny number, any number divided by a teeny tiny number, gets huge, but this one is also going toward positive infinity because, again, it's a positive divided by a positive. So what does that mean? Is the limit from the left equal to the limit, or as x goes to 0 from the right? Is the limit from the left equal to the limit from the right? And the answer is yes, they are. Look at that. They're both going toward positive infinity. So therefore, your conclusion would be that the answer to this question, what is the limit as x approaches 0 of 7 over 3x to the power of 4, the answer is going toward positive infinity. The limit does exist. It really does. That doesn't always happen, but in this case it did. So if you end up, let me stress that again, if you end up with some kind of a number, any kind of a number, any non-zero over 0, this is the technique that you have to use. All right, limit from the left and the limit from the right. It's the only time that you algebraically have to work out both limits like that. All right. For B, I'm going to suggest that what you do there is simplify this one first. Let me just kind of put a line under that. For B, simplify this into the limit as x approaches 0. Now, like I say, there's nothing special about the approaching 0 part. What if you had a function like 7 over x minus 3? Then x can approach 0 no problem. And in fact, your result would just be negative 7/3 if x approached 0. But here, you get the 7 over 0 if x is approaching 3. All right? So it's not what x is approaching that's important, it's the result you get that's important. So change this one. Just what I mean by that is simplify this x over x to the power of 3. So call this 5 over 2x squared. I'll leave that one for you to try. But again, remember what you do. You have to look at the limit as x approaches 0 from the left, and you have to look at the limit as x approaches 0 from the right. Now I am going to try C with you. I'll do that one with you. All right. And again, if you tried direct substitution right away, you still have an 8 on the top, but on the bottom you would have 2 times 0 to the power of 3. Well, by golly, look at that. That's a 0. Now, as soon as you see that, a non-zero over 0, now you have to look at the limit from the left and the limit from the right. So watch what I do. The limit as x approaches 0 from the left. Now remember, approaching from the left means that x is actually negative. Over, goodness, that's a weird line. Over 8, over 2x cubed. Now think about what you get. The top is still going to stay 8. That's not going to change. But the kind of numbers you're plugging in is a very teeny tiny number, but it's going to be a negative teeny tiny number. So when you plug that negative teeny tiny number in here for x and you cube it, folks, it's still negative. A negative to the power of 3 is still negative. So even though the denominator is going to become smaller and smaller and smaller and smaller, it's going to be a small negative number. So 8 on the top is positive. The denominator is going to be incredibly tiny, yes, but by golly, it's going to be negative. And a positive divided by a negative, this is approaching negative infinity. All right. Well, let's try the limit now as x approaches 0 from the right-hand side. So this would be my second calculation. The limit as x approaches 0 from the right of 8 over 2x cubed. All right. Now the top is still going to be 8, no question. But now you're plugging in a very tiny positive x value. And if you plug a very tiny positive x value in there, it's going to get even tinier when you cube it. And 2 times that is still small. So 8 divided by a teeny tiny number. Well, that's going to be infinity, but is it going to be positive or negative this time? Well, a positive x value cubed is still positive. Look at that. So now, positive divided by a positive is positive infinity. Are they going toward the same place? The answer is no, they're not. So therefore, we can conclude here for C that the limit as x approaches 0 of 8 over 2x to the power of 3 does not exist. It does not exist. Okay? D, I'll leave for you to try as well. Now, by the way, once you do a few of these, once you practice a few, you kind of catch on to what could be considered shortcuts. All right? So you try those other two. And there's one other case now that we have to have a look at. Now, and again, this talks about as x goes to infinity. All right? So this is the fourth, or fifth, and final type of limits that we're looking at. And the first thing they want you to notice is something that we've already seen, because this is a reasonable answer. What is the limit as x approaches infinity of 1 over x? So if you took 1 over a huge number, put in a whole bunch of nines to 100 nines or something, and if you type that into your calculator, do you know what you're going to get back? You're going to get back a 0. Even if you take 1 over x squared and plug in a very big number on the bottom, well, folks, that's going to become 0 as well. And here's some tables to verify that. It doesn't matter if the numerator is 1 or 10 or 100. As x goes toward infinity in the denominator, you end up with 0. So that's important to remember. You need to know that for what we're doing here now with this next lesson. All right? Here is the general result right there. But that, I consider that to be a reasonable result, reasonable answer. There's no algebra required. I mean, you know that if you have a number over an incredibly big number, well, folks, that's going to be very, very tiny. All right? So this result here now, what happens if you try direct substitution and you end up with the other weird, unreasonable answer? What if you get infinity over infinity? All right? What happens there if you try direct substitution, and that's what happens? Well, what you do is, here's some examples right there. You divide the numerator and the denominator by the biggest power of x that's in the denominator. Now, the explanation they have here, they've got an error in it. So I'm going to tell you what the error is, and I'd like you to fix it. To evaluate limits as x goes to infinity, where there are x terms in both the numerator and the denominator, start by dividing both the numerator and denominator by the highest power of x that appears in. Now, there's the mistake. That should not be expression. That should be the word denominator. So could you change that, please? Change that to denominator. Not necessarily the biggest power of x in the expression. Look for the biggest power in the bottom, in the denominator. All right? There's a reason for that. Here's example 7. Let's try this one. Now, what's going to happen is, if I just try direct substitution, if I just plug it in, which is what you should always consider doing first, you're going to end up with infinity squared. Oh, by golly, that's still pretty much infinity, isn't it? Infinity squared plus 1. I'm pretty sure that's still infinity. The denominator becomes 2 times infinity squared. Well, that's even bigger. Plus 3. Well, that's infinity. So whenever you see this result, infinity over infinity, that's when you ask yourself, well, what do I do here? You divide everything in the expression by the biggest power of x in the denominator. Now, if you look at that carefully, in the denominator, the biggest power is x squared. So what I'm going to do is divide by x squared, or think of it as, you can also think of that as multiplying the top and the bottom by 1 over x squared, you see? Now, why am I doing this for? Well, there's a reason for my madness. There's a method to it. So this becomes the limit as x approaches infinity, all right, of, now, multiply both of those terms by 1 over x squared, which means you're dividing by x squared, and do the same thing with the 2 terms in the denominator. Now, x squared times 1 over x squared, well, that, ladies and gentlemen, is a 1. and then there's a plus. 1 times 1 over x squared is 1 over x squared. So there's your numerator. Now, let's do the same thing with the denominator. 2x squared times 1 over x squared. Well, the x squares will cancel, and you're just left with a 2. And then there's a plus. And then 3 multiplied by 1 over x squared. Well, nothing cancels, so that's 3 over x squared. And now you use your direct substitution again. Now you just plug it in. And what happens is, of course, if you plug in infinity for x squared, this becomes 1 over a huge number. That goes to 0. That becomes nothing, 0. And the same thing with 3 over x squared there, right? You plug in a huge number. You plug in infinity for x, that goes towards 0. So look what you're left with. 1 plus 0 in the numerator, 2 plus 0 in the denominator. Now you remember you just used direct substitution again. And if I'm not mistaken, ladies and gentlemen, look what you get back. Now, isn't that amazing? The limit does exist. And it actually goes to 1/2. That's the y value that this function will get closer and closer to. Bigger you make x. And as x goes toward infinity, it'll never get to infinity. It's too far away. But as it gets closer and closer to infinity, the y value gets closer and closer to 1/2. Now, the other questions that are there on that page, they're basically the same thing. All right? B, C, and D. If you just try direct substitution, look at this. You're going to get infinity over infinity. C, yeah, you're going to get infinity. Well, actually, you might get infinity over negative infinity there, but you have to examine that one carefully because it's going toward negative infinity. Don't let that fool you. Don't let that throw you out. D is also going toward negative infinity. But divide everything by x to the 5 for D. Here, just divide everything by x. That's the biggest power of x in the denominator. Don't divide by x squared. And for B, x to the 7 is the largest power of x in the denominator. You divide everything by x to the power of 7. Or multiply by 1 over x to the power of 7. Same thing. All right? So I'm going to leave those for you to try. And then on page 15, ladies and gentlemen, there's a whole bunch of practice ones. All right? Now, look at all of those. Try direct substitution first for every single one of them. See what happens. See what you end up with. Do you get something reasonable? Because if you do, if you get back a reasonable answer, that's your limit. If you don't get back something reasonable, then you have to, depending on what you get back, try algebra or something like that. You can try to divide top and bottom by the biggest power of x if you get infinity over infinity, depending on what you end up with. But I want you to try all of these. Now, there's your answers right there on the bottom of page 16. Okay? So you can try those. And number 2 and number 3, I'll leave those for you to work on as well. Look at that, a piecewise function. Isn't that nice? Isn't that gorgeous? So anyway, that's it for the limits. I have done off, and I think I'm going to send this to everybody. I've actually done off a summary of what you should do for limiting techniques. Now, I just typed this up myself a few moments ago. Summary of techniques for algebraic limits. Always start by attempting direct substitution. Depending on the result of the direct substitution, here are the strategies you should apply. So number 1, if you just get back a reasonable answer, that's your limit. That's what you use. If you get back 0 over 0, well, then you have to try some type of algebra, usually factoring and canceling, although it might also involve, in some cases, multiplying numerators and denominators by conjugates. That's quite possible as well. Number 3, now this one is kind of reasonable. If you get back any number over infinity, like 1 over infinity, we saw that in a few cases, well, the limit is 0. That always happens anyway. So there's no workings to that one. Number 4, if you get back any non-zero number over 0, such as 1 over 0. In this case, you have to evaluate the limit as x approaches a from the left, and the limit as x approaches a from the right. Now, the result is always going to be either positive infinity or negative infinity, all right, depending on the signs. And finally, number 5, if you get back infinity over infinity, and again for this course only, because there are functions where you get back infinity over infinity, but what I'm showing you here would not work. There's other techniques beyond the scope of this course. Always divide the numerator and denominator of the expression by the largest power of x, which occurs in the denominator, and then try direct substitution again. Okay, so I think what I'll do is I'll send this out to everybody, so you have a copy of it, and that's it for limits. So I'll end this video here. I'm going to say half hour long. I'll end this video here, and when we start the next video, we're actually going to be doing something about tangent lines, and we're going to start a little bit of the fundamentals of calculus. Okay, so anyway, I'll stop there. That's it for this video. Bye bye for now.